Hello and welcome. In this video session, we will discuss on the POSIX semaphores. A semaphore allows the process or threads to synchronize the access to the shared resource. Semaphores also used to execute the critical section in an atomic manner. There are two types of semaphores, a named semaphore and a unnamed semaphore. A named semaphore has a name and it has a presence in /dev/shm on the Linux system, whereas an unnamed semaphore doesn't have a name and it resides on a memory location. Now let's begin the discussion on named semaphore. These are the list of functions those are used by named semaphores. They are semopen, sempost, semwait, semgetValue, semclose, and semunlink. Semopen is used to open a existing semaphore or to create a new semaphore. A sempost is used to give back the semaphore it holds, or sempost increments the semaphore value, whereas a semwait is used to decrement the semaphore value. Let's see more on sempost and semwait when we discuss the example. SemGetValue is used to get the value of the semaphore. Semclose is used to disassociate the calling process association with the semaphore. Semunlink is used to remove the semaphore. And when a semunlink is called, when all the process has used the semaphore, then the semaphore will be deleted. Now let's see the syntax of semopen. The semopen can be used in two ways. In the first form, it can be used when we are opening an existing semaphore, or the second form can be used when we are creating a new semaphore. So when we are about to create a new semaphore, we need to specify create flag and specify the mode in which we are opening, and when we are creating a new semaphore, it has a argument called as value. So here we have to initialize the semaphore with an integer value, which is a non-zero value. We will see what is the significance of having a value in the semaphore. So the semopen is similar to the open system call that we have seen before to open the normal file. If we specify the ocreate in the flag, then we have to use the mode and value arguments as well. Also, as a note, when we are opening a semaphore, most of the time the process opening the semaphore does a read and write operation on the semaphore. So we need to take care on the mode in which we open the semaphore. So usually the semaphore should be opened in a read-write mode. The value that is used here, this is an unsigned integer that specifies the initial value that is to be assigned to the new semaphore. Also, when a parent process forks a child process, all the semaphore that is present in the parent process is being copied to the child process, and the child process can utilize the same semaphores to synchronize between the child and the parent process. SemClose is used to disassociate the semaphore that is opened by the process, and on success it returns 0 and -1 on error. SemUnlink, a function, is used to remove the semaphore that is identified by the specified name, and calling this function, it marks the semaphore that to be destroyed once all the process stops using it. The syntax of SemUnlink is we have to include the semaphore.h, and we need to specify the semaphore name to which the process needs to unlink, and it returns a 0 on success and -1 on error. So now let's see the operations of the semaphore. A semaphore is an integer that the system never allows to go below 0. So we have seen that when we have creating a semaphore, we need to specify the value of the semaphore that is being created. For example, we have seen here that when a semaphore is created, it has a non-zero value. So a semaphore value cannot go below 0. Also, we have discussed previously that there are two functions that increments and decrements the semaphore value: SemWait and SemPost. SemWait, when successful, decrements the value of the semaphore, whereas the SemPost increments the value of the semaphore. We will come to know what exactly the SemPost and SemWait functions are used. So basically, when a process is executing a critical section and it needs a similar resource, it waits on a semaphore, and when it waits on a semaphore, and if the semaphore wait is successful, then it gains access to the critical section. Also, it decrements the semaphore count, and once the execution of the critical section is done by the process, it gives back the semaphore that it has hold by executing a SemPost function. By executing SemPost, it increments the semaphore value. So semaphore basically is a kind of a variable which is used among the process to synchronize the access to the critical section. So now we have a function called SemGetValue, which gets us the current number of semaphore that is present. Hello, now let's see an example of named semaphore. In this program, we have included the required header files, and the execution starts from the main function, and here we are taking a variable sem of type sem_t, which is nothing but a semaphore variable, and here we are using sem_open to open a named semaphore. So here the name of the semaphore always begins with the slash followed by the name of the semaphore. So in this case, the name of the semaphore is sem1, and we are creating a semaphore if it doesn't exist, and in this case we are giving a read-write permission for user, read-write permission for group, and no permission for others. And if you see this is the parameter which indicates the initial value of the semaphore. So now we are created by this, we have created a semaphore named as sem1 and with the required permissions, and its initial value is 1. So if the creation of semaphore fails, then we return the error, we display the error and we return, else we display that the semaphore is success. Now, when the semaphore is created successfully, its initial value is 1. So this is what we have created the semaphore with. Its initial value is 1, and in order we can get the value of the semaphore at any time by calling the function sem_get_value. Here we need to pass the semaphore, which is nothing but the pointer to the variable that is obtained from semopen, and a integer, the which here sval is the integer value, and we need to pass the address of the integer, and this function fills the value of sval by the current semaphore value. So now this prints the value equal to 1. So before sumWait we are printing the semaphore value which is in sval, so it should be 1 in this case because we have created the semaphore with 1 as the initial value. Now let's see the important feature of semaphore. So here the sumWait of sum, we need to call the semaphore in which we have obtained the handle, and when we call sumWait, if the semaphore value is greater than 0, then it returns immediately. If the value of semaphore is 0, then sumWait blocks until the value of sum is greater than 0. So in this case, if we run this program initially, then we have sum value equal to 1. Hence the sumWait doesn't block and it returns immediately. Now after performing sumWait, if we print the value of the semaphore once again, we will get the semaphore value which is decremented by 1. As we have discussed in the previous sessions that after the sumWait is successful, it decrements the value of the semaphore. So if the value of the semaphore was 1 before sumWait, after executing sumWait, the value of semaphore will be 0. So now once the semaphore is being decreased because of sumWait, now we are entering the critical section, and let's say that the process 1 is executing the critical section and it sleeps for 20 seconds, and here we are using sleep of 20 seconds. In this place there can be any other code running which refers to the actual use case of the critical section. Then after executing the critical section, we give back the semaphore to the system by calling semPost. So now after calling semPost, the value of semaphore which was 0 will be incremented by 1. So semPost increments the current value of the semaphore by 1. So whatever is the value of the semaphore, the current value of the semaphore will be incremented by 1. So in sumWait we decrement the value of semaphore by 1, whereas semPost increments the value of semaphore by 1. So now after we give back the semaphore, we print that the critical section has been executed, and after successfully executing semPost, we again get the value of the semaphore and print it. So in this case, once we give back the semaphore, then it would have incremented the value to 1. So now before running this program, let's see a similar program for process 2 so that we can understand the actual concept of semaphore. Now here we are opening the second program. Here we include the required header files which is same as the previous program, and here we are opening the semaphore. For example, we are opening the same SM1 semaphore. So the SM1 was created in the previous program using a oCreate. So now if we run this program first, then the SM1 will be created, and hence in the second program we are just opening the already existed semaphore in read-write permission. So as a very important note, we have to use the read write here because we are going to perform the operations, read and write operations, that is nothing but the sem post and sem wait operations on the semaphore. So if the sem open has failed, we print the error and we return. If the semaphore is successfully opened, we print the success status. So now after this, if we see the get value gives the current value of the semaphore, and then in the same way it calls a sem wait. When we call a sem wait, it checks for the current value of the semaphore. If the semaphore value is greater than 0, then it returns immediately, or it waits until the value of the semaphore is non-zero. So once it gets the semaphore, it enters the critical section and it executes the critical section. So in this case, we are given a sleep of 10 seconds, which is considered here as a critical section. The whole code is considered as a critical section in this. And then after executing the critical section, by calling sem post, it gives back the semaphore to the system, and by that we mean that the semaphore value is incremented by 1, and then we print the required thing. So now if we run process 1 and process 2, that is program 1, this is the program 1 and this is the program 2. If we run program 1 first, then as soon as followed by the program 2, the following things we can expect. So when the program 1 runs, it creates a semaphore by name sem1, and as soon as it creates a semaphore with the initial value 1, it performs a sem wait. So when it performs a sem wait, it gets the semaphore, and now when it gets the semaphore value will be 0 here. Then it starts executing the critical section, and now it sleeps for 20 seconds. Now meanwhile, if the second program started executing and it has executed the following statements and it has reached to this point, now the sem wait will block because the value of semaphore is 0, because the semaphore value was decremented in this case by the previous program 1, and hence the program 2 will wait until the semaphore value becomes greater than 0. So now after executing the sleep of 20 seconds, then the program 1 gives back the semaphore. As soon as it performs sem post, it increments the value of semaphore. By this, the statement which is blocked here will return, and it gets the semaphore. The sem wait will be successful, and then program 2 sleeps for 10 seconds and then executes. To understand this, let's compile the program and let's run it for better understanding. So now let's compile this. GCC -sem -lpth. So we need to link the semaphores as well using LP thread and minus object file. So for simplicity, I'm naming the program as P1. So the executable is P1 in this case, and similarly we will compile the second program and name the executable as P2. So now we have P1 and P2. So P1, and let's open the other terminal as well. So now let's open this terminal. So this is the same terminal as this what we have. So now in this terminal, let's execute P2 so that we can see the output parallelly. So now first we will execute program 1 output, then followed by that we will execute program 2. Now let's see what is the output of these. Now we are executing program 1 followed by program 2. Now if you see here, the program 1, the semaphore value is 1. This is the initial value. But once the sem wait is successful, we got 0 here. And now process 1 is executing. But if you see here, the program 2 is waiting until the semaphore becomes non-zero. So, so once the program 1 has executed the critical section, the process 2 has got the semaphore and it is now executing the critical section, and after 10 seconds it gives back the semaphore by executing some post, and it exits the program. So let's run the program once again. So here the program 1 runs and it opens this semaphore, and the name of the semaphore is sem1, and the initial value of the semaphore will be 1, and now the program calls a sem wait. As soon as it calls a sem wait, the semaphore value, since it is non-zero, it decrements the semaphore value by 1 and sem wait will be successful, and then it executes the critical section. And now meanwhile, when process 2 executes, it blocks on sem wait because the semaphore value is 0, and once the program 1 executes and gives back the semaphore, that is by performing sem post, then only the second program starts executing the critical section. So by this, the critical section, we are able to synchronize between the critical sections of both the programs. So now let's rerun once again. So you can see here, process 1 is running and it has acquired the semaphore. Now process 2 is waiting for the semaphore because its value is 0. As soon as the semaphore value is incremented, after the process 1 runs, process 1 posts back the sem post, the process 2 gets the semaphore and now starts executing the critical section, and then later it exits. So now we can also note that the semaphore that we have created will be stored in /dev/shm. So we can, sorry. So we can see here, we can see that this is the named semaphore that is created and it's present in the /dev/shm folder. And also we have one more function here to unlink. If we call this function, the semaphore which is present here will be deleted. So now let's call the unlink function. We will call the unlink function. Let's compile this program. So we have compiled this program and I will run only process 1 for now. So process 1 is running. It has created a semaphore by name sem1 and it executes for 10 seconds. Now meanwhile we have the sem1 in. So this is a named semaphore, as we have, it has a name in the file system. And now when the critical section has been executed and the program has called unlink, now let's see the content of this folder. So now if you see, there is no sem1 present here. So the unlink is used to remove the semaphore. So now this unlink function, by calling this, we have removed the semaphore name. So as an important note, we will be using the semaphore name. We have to use a slash then followed by the semaphore name, and we have to create a semaphore by its initial value, and then the sem wait, it waits for the semaphore. So the sem wait will be successful only if the semaphore value is greater than 0, and after performing the critical section, it gives back the semaphore to the system. So by performing sem post, it increments the semaphore. So here if you see, the number of resources is very important here. So the initializing the semaphore is done on the basis of number of resources. So now let's say that we have one resource and many process which wants the resource to execute. So now based on number of resource, we initialize the semaphore by the value. So here we have one critical section, in the sense like here we want one process to hold the resource at a time. So we are creating the semaphore value by 1. Now let's say that we have 3 programs running, program 1, program 2 and program 3, and let's say that any of the 2 programs can enter the critical section. So let's say we have a use case where any 2 program can parallelly execute the critical section, as we have identical number of resources. So now let's say that we have 2 identical resources available, and any 2 program can access the resource simultaneously. So now in this case we have 2 identical resource and three or more process running. So in this case we can create the semaphore by its initial value equal to 2. So now let's see the example of this. So now let's open third program. So this third program is similar to the second program. So here we open the same sem1 semaphore in read-write mode, and we try to get the value of the semaphore by performing sem wait, and if it is successful we print the return value and we perform the critical section. So critical section is not mentioned here, but we can have some lines of code to perform the critical section and then gives back the sem post. So now we have 3 programs, program 1, program 2 and program 3. Now if all the 3 program runs parallelly, only 2 programs can get the semaphore and execute the critical section, whereas the third program keeps on waiting for any of the program to increment the semaphore. So that once any one of the program gives back the semaphore, then it takes the semaphore and executes the critical section. So now let's compile this program as well. So we have named the third program executable as P3. Now let's decompile program 1. Okay, now we have program 1 and let's execute program 2 and let's execute program 3 as well. So now when we run all the 3 programs in the sequence P1 followed by P2 followed by P3, so now we have created a semaphore's initial value as 2. So any of 2 programs can get the identical resource and execute the critical section, whereas the third program will wait until any of the previously running program gives the semaphore. So now let's run this in order to understand. Now we are executing P1, then P2, then followed by P3. So now if you see here, P1 and P2 have got the semaphore and executing the critical section. So program 1 and program 2 is executing the critical section, and now P2 gave the semaphore and process 3 is running. So process 3 and process 1 was running. So now this means that program 1 and program 2 was running, and because we have created a semaphore with initial value equal to 2, So process 1 got the semaphore, process 2 also got the semaphore. Now once both the programs have consumed the semaphore, now the semaphore value was 0. So the third process was waiting for the semaphore, so that once the value of the semaphore becomes greater than 0, it gets the semaphore and then executes. Let's rerun once again. So now let's run P1 followed by P2, then followed by P3. So you can see this P1 and P2 both have got the critical section, whereas P3 is waiting. Now P2 gave the semaphore and that is acquired by the P3 and it executed. And P1 is also it executed the critical section and returned the program. So by this, what we can conclude is a semaphore is a variable which stores which has a integer value in it when we initialize, and the integer value specifies that the identical number of resources are available, so that the different process which are running can acquire the identical process and then execute the process. Meanwhile, the other process which needs the identical resource needs to wait until the identical resource is free and then obtain the identical resource and then execute. Hello and welcome. In this video session, Hello and welcome. In this video session, we will see the concept of unnamed semaphores. In the previous video session, we had seen the named semaphores. So basically, a named semaphore is a semaphore in which it is present on the file system, whereas an unnamed semaphore is one which is present on the memory. So when we say it is present on the memory, it is similar to the variable and it can be present on different memory segments. So unnamed semaphore can be used within the process and can be used to synchronize between different threads. In this case, the unnamed semaphore should be kept in the place where it is accessible to all the threads. That is nothing but a global memory area. So similarly, unnamed semaphore can be used to synchronize between different threads of different process. So in this case, the unnamed semaphore should be placed in a memory where the memory is accessible to both the process. So in this case, the shared memory is the place where two different processes can access the memory. We will discuss on the shared memory in next video session, but for now we can think shared memory as a part of a segment of a memory which can be mapped or accessed across different processes. Hence, the unnamed semaphore is a memory based semaphore and it does not have any name. In an unnamed semaphore, it has the same operations as named semaphore, like semWait, semPost, semGetValue, but an unnamed semaphore can be created using seminit and is destroyed using semDestroy. So seminit and semDestroyed are used only for unnamed semaphores and should not be used for named semaphore. Similarly, semWait is used to get the semaphore. So when semWait is successful, it decrements the value of the semaphore. When semPost is successful, it increments the value of the semaphore, and semGetValue gets the current value of the semaphore. So these operations are similar for named as well as unnamed semaphore. Now let's see what exactly is seminit. So this is the prototype of SemMinute. So a SemMinute is used to create a semaphore, and it takes the parameter sem of type pointed to a variable of type sem_t, and we have a int p shared. We'll see what exactly is a p shared, and this is nothing but the initial value with which it is created. So if SemMinute is successful, it returns a 0, or if SemMinute is failed, then it returns a -1. So in the previous, we had told that a unnamed semaphore can be used within the process to synchronize between the different threads. So in this case, we have to pass a 0 to p shared, and if we are creating a unnamed semaphore to synchronize different threads that are running in different process, then we need to specify p shared as 1. So this is the place where p shared comes in picture. So when p shared is 0, then the semaphore is to be shared between the threads of calling process, and if p shared is non-zero, then the semaphore is to be shared between the process. And sem_destroy is used to destroy the unnamed semaphore. So now in next, we will see some examples of unnamed semaphore. Now we will see the example of unnamed semaphore. So in this program, we have included the required header files, and here we have a global variable called as glob, and its initial value is 0, and we have created a variable sem of type sem_t. So sem is basically a semaphore variable. Now we have created a thread function called threadfunc, and the basic intention of thread function is to increment the global variable glob 10,000 times. So here basically, before incrementing the variable, global variable, so we put a semaphore, we wait for a semaphore, and once the semaphore is obtained, then execute the critical section. So this is the critical section in this case. That is nothing but the incrementing the global variable. And once the global variable is incremented, the sempost is called to give back the semaphore that is obtained. And now let's see the main function. So the main function begins with creating 3 threads, T1, T2 and T3, and we are creating a thread T1 and calling threadfunc, and creating T2 and calling threadfunc, and finally creating third thread T3 and calling threadfunc. And to each of the thread functions, we are passing the argument thread1, thread2 and thread3. So now once 3 threads are created, we are creating a unnamed semaphore. So here SemMinute is used to create an unnamed semaphore, and we have to pass the address of the semaphore variable, and in this case we are using 0. 0 implies we are using the synchronization of threads within the process, and value 1 here implies that the initial value of the semaphore is 1, and if there is a -1 on return if SemInit calls -1, then we have an error creating the semaphore and we exit. So finally, if the SemInit is successful, we wait for all the 3 threads by joining pthread join of T1, T2 and T3. So this makes sure that the main function waits for all the 3 threads to terminate. Then only the main function destroys the unnamed semaphore. So now in this case, we have one code segment that is shared by 3 threads. That is nothing but T1, T2 and T3. Now in this case, the expectation would be, we have initially the global variable will be 0, then each thread increments the global variable for 10,000 times. Before incrementing, it takes the semaphore and increments the count to 10,000 and then gives back the semaphore. So the thread which runs takes the semaphore and then increments the global variable and gives the semaphore. So at the end of all the 3 threads, the value of the global variable would be 10,000 into 3, that is nothing but 30,000. So let's compile this program. So here we can see that there is a thread synchronization that needs to be taken care. So for this purpose, we are using a unnamed semaphore. So now let's compile this program. So here we are compiling the program GCC one underscore the name of the program and linking using LP thread, and the output file we are creating is unnamed. So let's compile this. So now we have created a object file, output file as unnamed. So now let's run the program. So after running, we can see that by end of the program, the global value of the global variable is 30,000. So here, using an unnamed semaphore, we are able to synchronize between the 3 running threads. So here, thread 1 was running and it availed the semaphore. So when it availed the semaphore count which was created by 1 was now 0. So sem weight, the thread 1 called sem weight, and the value of semaphore is 0. Since the value of semaphore is 0, the other thread which are running is not able to get the semaphore, and hence they are not able to execute the critical section. So now thread 2, once the thread 1 finished executing, it gave the semaphore by executing sem post, and as a result the thread 2 got the semaphore and it executed the critical section, and now the thread 2 has given the semaphore, and hence as a result the thread 3 which is running is availed the semaphore and it executed the critical section. So now there is a sequence of execution so that any thread which gets the semaphore, it executes until it finishes the critical section, and then it gives the semaphore or it increments the semaphore so that the other thread can get the semaphore and enter the critical section. So in this case, when any thread gets the semaphore and enters the critical section, so no other thread can enter the critical section until the thread which has got the semaphore has released the semaphore. So now let's see an simple example. So in this program, let's do some changes and see. So now here we have created a semaphore with initial value equal to 1. So now let's say if I create a unnamed semaphore with an initial value equal to, in this case, can we guess the output of this program? Let's compile this. Now let's run the program. So when I run this program, the expected result will not be 30,000. That is, the global variable will not be 30,000. Let's run it to understand. So we can see that every time we run the program, it gives different result. So sometimes it can be 30,000 as well, but the value is not consistent. So every run we are getting a different value. So here we got 30,000, but in this case we got 27417. So next run we got 25673. So the explanation to this output will be as follows. So in this case, we have one critical section, and so in this case, when we have one critical section and we have created a semaphore by count equal to 2, so what happens is any 2 threads can simultaneously enter the critical section. Hence, the global value will be altered, or it gives an unexpected result. So since we have one critical section here and we want only one thread to enter the critical section, so we should have a semaphore with count equal to 1. Then we will not have a synchronization issues. So let's change this back to 1, and now let's compile the program once again. Now let's run the program. So now the any number of time we run the program, we get the same result, that is 30,000. So now we are able to achieve the synchronization between threads within the process. Hence, we are using a unnamed semaphore. So by using a unnamed semaphore, there is no entry in the file system. That means we are not creating any semaphore by a name, and it does not have an entry in the file system.